re-energized for our next session of fantastic speakers. Now, we're going to have Young Scientist session, and we'll be joined by young scientists from various esteemed establishments like DRDO, IIITD, and Christ University. I now have the pleasure to introduce Dr. Santu Sardar, a distinguished scientist who joined DRDO in 2010. He currently serves as a director of DRDO Young Scientist Laboratory for the Quantum Technologies, a lab dedicated to advancing quantum technology.
Well, thank you for inviting me in this symposium. It has been a very good 2 days, and on top of that it's a post-lunch session. So I will try to complement the information that was being exchanged and presented by various speakers. So my topic will be on what DRDO is doing in quantum technology. Very brief information about some of the aspects of global scenario that was mostly based on computing. And then I will explain the quantum advancements that DRDO is leading and our lab activities, along with that summary of DRDO. So, quantum technology is the new technology frontier, as we know. So, due to its importance, there are worldwide lots of efforts on quantum technologies. As you see, most of the most prominent is from China, and then we have Europe and US. And there are other few countries, small countries also, they are coming up with big investments in quantum technologies. And recently, India, they have also announced their national quantum mission. So the data is a little older. It's in the summary of 2023, but we will get the idea. Now let us come to quantum computing. So quantum computing, implementation of a quantum computer is not very old idea. In fact, the first it was proposed in the year 1980 by a mathematician Yuri Manin, and then it was gradually took off momentum. And Richard Feynman was the first who actually promoted and accelerated the idea that we need a logical quantum computer model. He proposed a presented one, and he explained very meticulously about why classical computer may not be sufficient for some of the applications and techniques. So it is in the year of 1980 and 1985. So from then onwards, there are good amount of efforts started in both government as well as in private sectors like IBM, etc. But still, we are in a very nascent stage. So as you see this. So as you see in this graph, currently we are in a very beginner's situation. So today our quantum computers are not very well capable, but it's in a very nascent of child state, we can say. But there is a promise of quantum advantage where classical computers cannot do some problem statement which quantum computer will be able to solve. So due to this anticipation of these opportunities, lots of investments have been in these directions, and lots of technologies and implementation strategies are being explored to implement quantum computer in a big scale. In these directions, we have recently seen the announcements of Google, that is the Willow processor, which is a number of qubits present there is around 105. And the good thing is that they have consistently explored towards cheapest quantum processing unit. And this quantum processor, Willow processor, they have made in their own dedicated quantum computer fabrication technology in Santa Barbara. And people have seen the details already. And another very prominent exploration going on in case of quantum technology, that is in China. Both these explorations are on superconducting circuit-based quantum computers. And same is with IBM. IBM had a very aggressive roadmap earlier, but recently they have updated their roadmap and they are focusing more on interconnections and good quality of qubits instead of number of qubits, along with more interconnections and more number of gate operations. Now, not only these big players, but there are various other sources available who actually offer quantum computer. Though it's a very small scale quantum computer, but they offer it as per their services. And we can see that this data is slightly old, but we can get an idea about who are the major players in these directions. most of the application, most of the implementation of qubits are on superconducting circuit based and silicon based. But however, these companies are for-profit institutions. So basically, there is a doubt how much knowledge exchange will be there and how much visibility will be there. At the same time, globally, if we see lots of export controls are also creeping in quantum technology. So there is a Western Arrangement Export Control regime is there, which contains 42 member states, basically countries, and mostly all the major countries are there other than China and Israel, and they are proposing lots of controls specifically on quantum computing technology and its components, speech, etc. But as we seen in the earlier, so these are very small scale quantum computers, so the export control is prominent in this stage itself and it will grow further. But we will have to have lots of way to go to actually use quantum computer for practical applications. As per this survey, if we see, we will be needing around hundreds of thousands of qubits based processor to use it for actual practical applications. But still, it's a good way and good start. And at the same time, due to this export control regime, we have to have our indigenous efforts in these directions. I'll come to it, how actually DRDO is working towards it. Now, as was being told in the brief speech by Dr. G. Raghavan, how actually quantum computing and quantum communication are related. So he just briefly touched upon. As we know, quantum computer, other than the applications that I have already shown, one good direction where quantum computer is good at is for making the encryption, RS encryption specifically. So this is actually proved algorithm is already there. And when we have a powerful enough quantum computer, ideally we should be able to do it. So and this actually will create lots of difficulties and cryptographic vulnerability, which will lead to various scenarios and worst case scenarios as well, like power grid shutdown, breakdown of banking systems, battlefield tactics could be jeopardized, satellite hacking, etc. There are many other possibilities. Now, due to this reason, actually the quantum safe cryptography actually became more popular. So there are two kinds of it. One is post-quantum cryptography, other one is quantum key distribution or quantum cryptography. There are other branches of it as well. And for cryptography, as we know, we need random numbers. For that, quantum random number generator is also a very prominent technology nowadays. However, quantum cryptography actually it started long before. Before actually the quantum computer implementation was conceptualized in the 1980s. So basically, the first work related to quantum cryptography that was later came in the literature, that was started in 1968. But actually, initially it faced lots of rejections, and in 1983 actually the paper was published. It was by Stephen Wessner. He actually gave the idea that was at that time it was not for cryptography but for quantum money or something he was saying. But then that idea was applied to cryptography using Bernard and Bennett and Broussard. They also faced lots of rejection initially, but in 1984 in the IIC conference they published their first paper on QPD protocol, which is called BB84. And after that, actually, this domain also exploded. There are lots of activities going on in quantum key distribution area, both in fiber-based as well as in free space-based. So fiber-based, currently using networking, people are extending the distances, and in free space, the final target is for satellite-based quantum key distributions. And for that, globally, lots of projects are already going on. However, there is a difference between theory and practice. So, these device imperfections and due to some other issues, there are lots of problems to solve in quantum key distribution as well. And before we conclude, so just one slide related to quantum sensing. So this is, though not related to computing, but this is a very prominent technology, and we can have short range, good deliverables and applications related to quantum sensing. But if we see, there are many common blocks related to quantum sensing which you can utilize across multiple quantum sensors. There are lots of quantum sensors, But the basic building blocks like optical systems, lasers will be there. Then you will have an atomic core which will be excited by lasers or by some other means. And this will be supported by our electronics, and on top of that algorithm softwares. And we have to have knowledge of RF and microwave as well in this direction. And these common building blocks we can make use to develop multiple quantum sensors like magnetic sensors, gravity, navigation, atomic clock imaging, quantum radar, just to name a few. And this is basically an assessment by US DOD. So I will not go into the details of this, but related to computing, what they are projecting that. So this block, this actually is for small noisy quantum computer. Basically we are in almost in this phase now. And this block is our large error corrected quantum computers. And this purple means basically it's a standalone system which can make a difference. We need not integrate with other systems to get their advantage. So as you see, small noisy quantum computers, it is currently in the lab demonstration phase, and it has a potential military impact which is very less. But if we can make large error-corrected quantum computers, which is not available at present, but explorations are going on, then we can have an existential impact on the defense sector as well. So this is some of the inputs related to our global scenario. Then I will come towards our quantum advancements, what is going on in DRDO. So DRDO has two major approaches on quantum technology. We are exploring communication, various aspects of application, sensing, computing, cryptology and basic technologies to support this vertical. But our approach is twofold in parallel. One is to leapfrog by developing system level or prototype level demonstrations using COTS components and other systems so that prove the technology. At the same time, how we can indigenize the individual components and subsystems. So that those explorations are going also in parallel. We had our own quantum roadmap in the year 2019 itself. It was approved by our secretary, sir. And as per that, these are the thrust areas. So quantum communication, we have fiber and free space QKD and networks. We are measurement device independent QKD that we are already exploring. Then our another target is high altitude platform based QKD. In computing, indigenous quantum computing solutions development, algorithms for cryptanalysis, and cryogenic control of the qubits, scalable qubits. In sensing, major target is magnetometer, clock, navigation, and in addition we are exploring imaging and radar technology also. Post-quantum cryptography is also being explored, and there are various common technologies which is classical, but that will be very helpful when you go to lab level to system level and application level. So those are also as part of basic research phase. Now I will come to our lab. So DYSL-QT, DRDO Young Scientist Lab on Quantum Technology. This is a very new lab. It is in this campus, DIIT. It started in the year 2019, April 2019, with a few young scientists. It was a brainchild of our Honorable PM, Sri Narendra Modi ji. So idea was that we will put young scientists in a lab and give them challenging opportunities. So there are 5 labs. Among them, one is DYSL-QT working on quantum, and other 4 they are working on other technologies. Now our secretary sir made one apex committee as well, who actually will guide us in the technology direction. We are total 11 scientists at present working in this lab. And our main focus is on only these 3 activities. One is quantum computing, specifically superconducting circuit-based full-fledged quantum computer development. Another is atomic magnetometer. Focus is on mainly bringing the atomic magnetometer prototype with high sensitivity from lab field. Quantum random number generators, we are exploring various flavors of it. And quantum key distribution. At present, mostly we are focusing on compact solutions with crypto interface for fiber-based QKD, but free space QKD related explorations also going on in DRDO. So these are the 4 activities in our lab. So I will mainly focus on our computing activity. So this activity started in the year 2021, or at the end of 2020 it was conceptualized. And we started this activity in collaboration with TIFR Mumbai. And our target is to develop a full-fledged 6-qubit quantum computer. Full-fledged means basically the idea is that we should be able to access the quantum computer through cloud and do the operations and then get the information through the user interface. In the back end, all the activities we will be doing as part of this project. So here we have our own cryogenic setup. So the cryogenic setup, we will have a quantum processing unit. Then we will have control and measurement circuits, and this automated calibration software that is actually do offline processings of all the qubits, and this we have to have periodically. On top of that, there will be a software layer, and then on top of that, there will be a cloud access. So now in that, these are 3 collaborations with DYSL Mumbai, and at the same time, the cloud access or cloud interface is being developed by TCS. So here so this actually shows an individual qubit, and this is the qubit structure that we are using. So in this, actually the 6 qubits are housed at present, but there are 12 possibilities for 12 qubits. And then this qubit structure is mounted inside the dilution freeze. So this bottom cylinder, it is inside that. And this is the overall setup of our, so this is the dilution refrigerator. At the bottom of it, we have a quantum processing unit, which was fabricated in TIFR Mumbai. And then we have RF connections with the outside control electronics rack. And on top of that, we have our software layers, and then we have the cloud access. So this is in a very final stage at present, and most probably by early this year, we'll be able to release the quantum computer for normal public to access and do gate level operations. Now, what are the indigenous efforts that we are putting into in this quantum computer? First of all, the quantum processing unit that is designed and fabricated in India. On top of that, in parallel to our standard control electronics rack, we are trying to miniaturize it and make a FPGA-based solutions. So for that, we have already tested with not only 1 qubit but multiple qubits also, physical qubits, and this caused lots of significant size reduction as well as cost reduction as well. So basically this qubit assembly and then this control, though it is control electronics, but it will do all these 3 activities: initialization of the qubits, control, measurement, and what is not mentioned here, it can do calibration of the qubits periodically as well. So how actually our complete structure will look like? So basically this will be the gate level design that user can design and fire in the software interface. Then it will come to our internal software where actually we will transpile the code, we call it QASM, and then that actually will give input to our, after some processing, we will give input to our FPGA board where actually we will be developing the RF pulses which will go to the fringe, to the quantum processing unit. So this, it was a video. Okay. So basically it will be a string of RF pulses which will be sending to the qubits for their control. And after that, separate RF pulses will be given for measurement after the operation is complete. And then the output will be flashed in our user interface as well. So as we know, quantum computer, the output will be the measurement, the operation is statistical, the output will be statistical in nature, we have to interpret the data. So another indigenization effort that is going on in this activity is how to indigenize some of the major components, that RF components specifically, which is used in this quantum computer. So instead of using the RF mixer, packaged RF mixer, we tried to procure only the chip, and they made the RF mixer assembly jointly with TIFR and DYSL-QT. That also caused significant cost reduction by a factor of 10. At the same time, we have a very good facility called GATEC in Hyderabad in DRDO. So there we are trying to make hemp-based LNA, which will work in cryogenic temperatures. That also we have made multiple rounds of tests in our quantum computer setup itself. So this is also a work in progress. Another activity that is going on as a collaboration with IIT Bombay. So this activity is mainly being executed by IIT Bombay, where they are using different approach to implement quantum computers. So here we are talking about superconducting circuit based. So they are using quantum dots, silicon quantum dots to implement the qubits. So it's a silicon germanium metal structure. They will make a potential well, and inside that they will trap a single electron which they will use for as a qubit. So that activity is also going on in a good directions, and the PI has fabricated 2 qubit devices also, and currently the testing is going on, qubit characterization is going on in the setup. Now this is as per the quantum computer implementation activities going on in DRDO as far as concerned, so summary. But I would like to take this opportunity to explain or summarize some of the other activities going on in our lab. So one such activity is on atomic magnetometer. So our idea was to first prove good sensitivity magnetometer in lab, and then bring the magnetometer prototype from lab to field and test it for a practical application, specifically for naval applications. So this was our first effort jointly with TIFR Hyderabad. So in the shield environment in the lab, we have achieved sensitivity which is around picotesla level. And but this is a lab level prototype. We have to bring it from lab to field. So for that we have to get rid of the shield, and after that we have to get rid of lots of components. We have to compact it and make a very small compacted sensors. So for that we have made our own coil, which will not only mitigate the arc magnetic field, at the same time it can impart controlled magnetic field also, and various other activities. So using that, this is our lab setup without shield. And then we have made this small prototype where actually all the other components related to the sensor. So this is the balance detector. This was the 3D printed diagram of the 3D print, and this is the 3D printed structure. So in that, all the optics and the detectors, those are there. So it's a small pencil box size of sensor package. And electronic subsystem is separate. That anyway in the practical situation it can be remote also. So that we just started field testing of this magnetometer. Just I wanted to mention. And where we stand in terms of sensitivity, so we are at par with the global standards, global status. So these are some of the industry who actually supply atomic magnetometer, but however there are lots of restrictions, and their finest versions are not available always. Another activity we are working on, quantum random number generators. Initially we made a prototype of QRNG, this one, and then we gave TOT to a private industry. And in parallel, actually we have tested exhaustively in a setup in the Anand Parbat military station in Delhi, in the army area. And after that, the industry, they are getting lots of requirements from the armed forces, and currently we are working on enhanced versions of the QRNGs, 4 flavors: branch path based, time of arrival, laser phase noise, and vacuum fluctuations. So at most we have gone up to 160 Mbps at present, but there is potential to go even further that we are exploring. Another activity is on quantum key distribution. So this activity started in 2018, which was led by Mr. Amit Srivastava sir, RCI. He is also here. So there our effort was to do the field testing of quantum key distribution with 2 different protocols. So initially we tested in a limited sense around 10 to 12 kilometers between 2 DRDO labs in Hyderabad. So from that we got some of the inputs, and which actually helped us to enhance the system so that we can test it in field for more than around 100 kilometers. That we tested between Prayagraj to Vindhyachal with actual laid down fibers which was available from Intel. And there we have tested 2 different protocols, and we have simulated Eve and tested the performance or detection probability of that as well. So now we are taking it forward and making complex, compact QPD boxes, which is already interfaced with SAG certified crypto subsystems. Complete system will be certified by SAG, which will be readily deployed for armed forces scenarios. At the same time, we are collaborating with IISc Bangalore to develop measurement device independent QKD, where the distance coverage without repeater will be around 200 km we are targeting. At the same time, it will be a chip-based solutions. At the same time, with IIT Delhi, we are working on various aspects. One of them is hybrid entanglement, which will be focused on free space quantum communications, high speed free space quantum. There are various other labs in DRDO who are exploring various aspects of quantum, like cold atom interferometer that is being explored in RCI Hyderabad. In fact, this is one of the first activity that DRDO started in the direction of quantum technology before QKT. Then we have post-quantum cryptography care, Bangalore. They are working in this with strong collaboration with academia. And as I was saying, we are trying to indigenize some of the major components also. One of them is laser system. So for that we are working on pixel lasers. So that being explored by SSPL. And first prototype was developed, and that is tested in our magnetometer test setup as well. So just to summarize how DRDO is going in this from 2016. So our first cold atom project that was conceptualized in 2016. Then in 2018 we had our first QKT project. And in 2019 DYSL-QT was established, dedicated only to work on quantum technologies. In the same year, we had our own quantum roadmap approved by our Secretary Sir. And then, as you see in 2020, the 10-kilometer QKT demonstration that was in 2020. And in the same year, December, we have made our first QRNG prototype. And in the 2021, the cold atom was established, which the project which actually started long back. And in the 2022, the 100-kilometer field demo in Prayagraj. Our first atomic magnetometer field test, lab level testing, and our quantum computing activity started around 2020. So in 2022 we could able to demonstrate 2-qubit quantum computer and simple gate operation also we have demonstrated in our actual setup. Now going forward in 2023 we expanded our activity in quantum computing and made 4-qubit quantum computers, and we have demonstrated various gate operations. And by this time we have made our control electronics also. With that also we have tested in the actual setup with actual qubits. And in the same year we have made compact prototype for our magnetometer also, and microfabricated alkaline vapor cells which actually is useful on in various aspects of sensing, not only magnetometer but clock and other aspects also. The last year was very eventful. We have demonstrated in front of our Apex committee 6-qubit quantum computer, and currently we are actually trying to enhance the system performance even further before actually we launch it. Then we have made our lab demonstration. So lab demonstration of our atomic magnetometer that was completed. We pushed the limit up to around 500 femtosecond also, and that also was demonstrated in lab. And in QRNG we have made compact systems that around hundreds of Mbps, and that we have given to SSG for their independent evaluation. And in defense, if we see other than DRDO, there are related to quantum technologies. Then we have MHOW, they developed quantum computing lab and AI center also, that is for the educational purpose of the armed forces. And this photo shows actually the company that are moving TOTs. They are basically promoting their products in front of various dignitaries. So, and now we feel that with our national quantum mission, the efforts in DRDO and other organizations, they will be much more coordinated, and we will proceed towards much faster progress in these directions. So I will conclude here. So basically, DRDO is determined to work towards indigenization, Atmanirbhar Bharat in quantum technology, which is a must, because ultimately, technologically, we have to be independent as much as possible. So for that, we need leapfrogging as well as in component level indigenizations, which we are already focusing on. At the same time, we need lots of collaborations, both in national and international. So I think in QM, they will be able to coordinate all these efforts together and focus towards a sustainable quantum ecosystem. So with this, I will thank you all for your patience. Thank you.
Thank you, Dr. Santu Sardar, for your enlightening presentation on advancements in quantum technologies. I would now request Ms.